Hi, everyone, and welcome to the second part of our spring break review packet video, the second video for our spring break review packet, part two. So we'll be taking a look at the remaining problems from the review packet. So with that, why don't we get started? Problem number one, again, this is a calculator question. The rate at which rainwater flows into a drain pipe is modeled by this function, R of t. And remember, R of t, you've got to remember, is a rate. It is a rate, and it's in cubic feet per hours. T is measured in hours, where T is going from 0 to 8. The pipe is partially blocked, allowing water to drain out of the other end of the pipe at a rate. Again, D of T is a rate, which is that function right there for 0 to 8. There are 30 cubic feet of water in the pipe at time T equals 0. Anytime they're giving you rates, remember to look for something that gives you an idea in terms of an application problem like this one, where you have something that says at a certain time, this is how much water is in there. A lot of times it's going to be the initial amount of water. Initially, how much, the initial amount that's there. So when T equals 0, what's happening? So, but it can be anything. They could say, oh, we know it's known at time T equal at time after 3 hours, the amount of water was equal to this. That could be the case as well. But in this case, they're telling you at time T equals 0, there's 30 cubic feet of water in that. You're going to want to make sure you have that. Next one. Part A, this one is worth 2 points. How many cubic feet of rainwater flow into the pipe during an 8-hour time interval from the 8-hour time interval 0 to 8? Okay, well, that's just a real basic one. Think about the relationship, how you can find that. Dealing when you have a rate, how do you find an amount? When we have a velocity, how do we find a distance, position? Same thing with this one. When we have a rate, how do we find that amount? The rate that water's coming in, how do we find the amount? So there's that one. In this next one, is the amount of water in the pipe increasing or decreasing at time T equals 3 hours? Give reason for your answer. In this case, you got to remember that you got two different rates here. One rate of water coming in, one rate of water going out. So that's going to have to come into play on that one. And again, this is 2 points. 2 points. 1 point for the calculations that you need, and 1 point for your final answer, whether it's increasing or decreasing, and your justification for that. Also keep in mind, in this problem, you do have information, so you can include units on these things. So make sure you do include the units as you're working on it. Okay. Part C on this one, at what time 0 to 8 is the amount of water in the pipe at a minimum? Justify your answer. Okay. They want to know where it's at a minimum. Now, you are on a closed interval. And because you're on a closed interval, that means you have to take into consideration other pieces of information. Remember, in order to do that one, you've got, if it's wherever you have a minimum in the times between 0 and 8, if you're going to have a minimum, it's going to occur at a critical value. Okay, but you also do have a closed interval, so that's coming into play as well. So you're going to want to work with that. And in this case, you get 3 points. 1 point for finding the critical values, 1 point for your final answer, and 1 point for the justification that you have in terms of when it's at a minimum. The next thing you have, part D, a pipe can hold 50 cubic feet of water before overflowing. For T greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Okay. All right, so in this case, you've got to go through, come up with this expression that can be used to find that one. Now, keep in mind, you got this part up here too. You do have that initial amount, how much water was in there at time T equals 0. And then you have working with this. Now, the other key part here is that they're telling you that these rates that we're working on, R of t and D of t, they apply they apply for t values greater than 0, is what they're basically telling you here, is that those same rates work when t is greater than 8. So we can plug those in. You get 2 points on this one, 1 point for the integral and 1 point for your equation that you have. So however you set that equation up is up to you, but you're going to need to come up with and make sure you include that equation. Next one, part number 2. Again, this is a calculator question, so you're going to want to keep that in mind. Use your calculator whenever it's appropriate. Quite honestly, on problems 1 and 2, anytime I'm asked to evaluate a function, unless if it's something that's real easy to evaluate by hand, I'll do that. But if I'm asked to evaluate a function or a definite integral or to take the derivative of a function and evaluate at a certain point, I'm going to use the calculator to do that. I just want to I want to write out what I'm doing and then go through and say what that answer is. So number 2, at time t greater than or equal to 0, we have a particle moving along a curve on the xy plane, has position x of t, y of t, with velocity vector v of t is cosine t squared and e to the 0.5 t. At t equals 1, the particle is at the 0.35. So this is kind of along the lines of those initial value problems. They're telling you that point there for a reason, and that's going to come into play real quick. Find the x coordinate of the position of the particle at time t equals 2. Okay, so really what you're finding is you want to find the value of x at t equals 2, and you got to think about what the integral tells you and how you can incorporate the integral with the fact that at t equals 1, you know the point, its location, to find that x coordinate of that point. For part B, there's a point on the curve at which the line tangent to the curve has a slope of 2. At what point is the object? At what time is the object at that point? Okay, so what you have to do on that one, remember for part B, that dy dx is equal to dy dt over dx dt. Okay, so you want to kind of keep that in mind, and we know in this case that is going to equal 2, and then it's a matter of solving that. So really, you're going to go through, once you know what this is, then you're going to be able to just plug that into the calculator and solve that one and get your value, get your answer for t. Okay, so you need to go through on this one. On this one, it's worth 2 points. 1 point for basically getting that the slope in terms of t, and 1 point for your final answer. Please also, as you're looking at that, keep in mind, remember your position is here, x of t, y of t, and your velocity is here. You want to think about the relationship between those two. That can help you come into play too. Part C, find the time at which the speed of the particle is equal to 3. Well, speed, remember, is really the magnitude of your velocity. So you're going to have to set that one up. Figure out, speed equals that magnitude there of the velocity vector. So use that to help you identify what your speed is at time t equals 3. And then part D, find that total distance traveled by that particle. Well, really, that's really the arc length of the particle. Okay, it's really the arc length of the particle. So of the curve that we're working with. So you have information there to go through and set that up. Think about how we find the arc length when we're dealing with a velocity like that, and you should be in pretty good shape. Now number 3, this one now we're getting into the non-calculator problems, okay? Johanna jogs along a straight path from t equals 0 to 40. Johanna's velocity is given by the differentiable function v. Select values of v where t is measured in minutes and v of t is measured in meters per minute are given on the table above. Use the data in the table to estimate the value of v prime of 16. In this case, that's at this point, I think you're recognizing that one as a pretty common problem when you're dealing with a table. Just again, you got units here. Make sure that the units come into play on this one. This one, part A, is 1 point. You get 1 point for coming up with that approximation for approximating v prime of 16 based on the table data. Part B on this one, using correct units, explain the meaning of that integral, the integral from 0 to 40 of the absolute value of v of t. Again, what you gotta be aware in this case, the difference between the integral of v of t, the difference in meanings between the integral of v of t and the absolute value of v of t. So be aware of those, be comfortable with those in terms of what that meaning is. And in this case, you get, and it is a right-hand Riemann sum with the intervals provided, the 4 sub-intervals indicated. So in this case, because it's a right-hand, you're just going to take the 2 consecutive and use the right-hand endpoint to go through and evaluate it. But in this case, for part B, it's 3 points. 1 point for the explanation and the meaning of that. 1 point for the right-hand Riemann sum, and 1 point for the approximation. And again, keep the units available. Make sure you do have those units in there, okay? Because they can take off points for not including units on this one. It's there. Part C, you got Bob comes along and he's riding his bicycle on the same path, and he's there for 10 minutes. Bob's velocity is modeled by this function here, where t is measured in minutes and b of t is measured in meters per minute. Find Bob's acceleration at t equals 5. Well, again, you got to remember, this is velocity. That's not position. That is velocity. So think about the relationship between velocity and acceleration. And you can then find Bob's acceleration at t equals 5. And then for part D on this one, based on the model B from part C, find Bob's average velocity during the interval from 0 to 10. Okay. The average velocity, it's really looking, this right here is your velocity function, so we want to find the average of that function. And remember, that's going to end up being the integral on that one. You have an average value function that involves an integral of that, so you're going to want to be working with that to find that particular one. So that should be enough to get you have a good finish on problem number 3. Number 4, this one's a little bit different for a slope field problem and a differential equation problem, because of the fact that if you take a look, they don't ask you to find the particular solution in this one, okay? And part of that, there's a reason for it, and the big reason is if you take a look at that differential equation that they give you on this one, that's one that's not going to be you can't separate that. You can't separate the variables. So this is not going to be one where you're going to actually go through and have to find a particular solution on this one. But you do have a slope field, so they're going to want you to, sketch the slope field for that differential equation at the 6 points that you have, at 0, 2, 1, 2, 0, 1, 1, 1, 0, negative 1, and 1, negative 1. Those are your points. The next thing, so on that one right there, you get 2 points for that. 2 points, what you're looking at, the slopes, basically you're looking at when the slopes are 0 and when the slopes are positive and negative. Okay, so keep that one in mind. Next one, part B, they want you to find that second derivative. Okay, well, in this case, remember on here that dy dx is 2x minus y. So we're taking the derivative of that. So you're going to have to take the derivative of this thing with respect to x. So d squared y over squared is going to equal the derivative with respect to x of 2x minus y. Think about what that means. And what you have to keep in mind is that your final answer needs to be in terms of x and y. So take your derivative, get your final answer in terms of x and y, and remember, you are taking the derivative with respect to x on this thing. So that's going to come into play there. And then and this one you get 2 points, one for that second derivative and 1 point for telling whether or not it's concave up or concave down. In terms of that, where it's concave up, where it's concave down, and what the reasons are for that. For part C, they're telling you y equals f of x is a particular solution to that differential equation. So they've already found that particular solution. You don't have to find it. Okay? You don't have to find it. You know y equals f of x is a solution to that. And we know that when you put 2 in for x, you get 3. So the 0.23 lies on the graph of f of x. And the question here is, does f have a relative min, relative max, or neither at x equals 2? Justify your answer. Keep in mind here, we're not asked to find f. We're just supposed to analyze f at a particular point. And you got to think about what it means to determine how you go through and determine if you have a relative min, a relative max, or neither at x equals 2. Okay, so be aware of that. And the next one here, find the values of a constant m and b for which y equals mx plus b is a solution to the differential equation. Here's the thing. You know the differential equation is 2x minus y, and we know that in this case, y equals mx plus b is a solution. And from that one right there, I know y prime is equal to m. So think about what that means, and what you're going to do is set up an equation that's going to allow you to solve for m and b. And in this case, for part D, it's worth 3 points. 1 point for just realizing that the derivative of that thing is going to equal m. 1 point for setting it up, working with that, with the problem, going through and coming up with an equation that you can use to determine m and b. And 1 point for your final answer on that one. So it's a lot of stuff happening here, but it can be done pretty quick. I think this one right here is a little bit more complicated than it looks a little bit more complicated than it really is. Now let's take a look at number 5. Number 5, in this case, we got a function. This is kind of an interesting problem. We have a function f of x where f is 1 over x squared minus kx, where k is a non-zero constant. And what they tell you is that the derivative of f is going to be given by this right here. So it's basically, if you go through and do the quotient rule on this, that this is what's going to end up happening in terms of the derivative. So you have your derivative. Now, the first thing they ask is let k equal 3. So this is what we have. This is our function. Write equation for the line tangent to the graph of f at the x coordinate 4. So in order to find the equation of a line, remember you need 2 pieces of information, point and the slope. Okay, so you're going to want to consider that derivative up there in terms of working with that. And this one you get 2 points. 1 point for determining the slope and 1 point for determining the tangent line to that. So the tangent line, the actual equation of the tangent line. For part B, let k equal 4, so that we're dealing with this function. Determine whether f has a relative min, relative max, or neither at x equals 2. Again, on this one, you're going to need to determine what's going on. Think about how you determine if you have a relative min or relative max, or neither. What you're looking at to make that determination. There's a reason why that derivative is there. So you're going to want to make sure to use that. And in this case, you get 2 points. 1 point for for how your process in terms of making this determination, and 1 point for your answer and justification that you have for it. Okay. Remember as well, when you do that justification, that you're very explicit about what is happening, especially when you're looking at for a possible relative max or relative min, what's happening to the left of that, in this case 2, what's happening to the right of 2, and make your explanation that way. Part C, find the value of k for which you're going to have a critical point at x equals -5. So again, you know what -5 is. You know x is -5. If you're going to have a critical point, that's telling you something about the derivative. The one thing you got to think about, though, is be aware of what the domain, as you're working on that, be aware of what the domain of the function is that you're working with, so that that you don't make some mistakes with that. Okay, you get 1 point for that, for your answer on that, for the critical point, for the values of k, for finding the values of k where we have a critical point. Part D, k is equal to 6. Find the partial fraction decomposition of that, and then use that partial fraction decomposition to find the integral. All right, so again, you want to remember with partial fraction decomposition, you're going to want to factor that. So remember, 1 over x squared minus 6x is equal to 1 over x times x minus 6. So use that, get your decomposition, and then go and integrate that. And in this case, you get 4 points. 2 points for the partial fraction decomposition that takes place, and 2 points for your antiderivative. Notice on this one, they're not giving you any initial value or anything like that. Don't forget the plus c. Okay, definite integrals, you don't have to worry about the plus c, but on something like this one, an indefinite integral, be aware of that plus c, because they'll go through and knock off points for forgetting that. So good luck with problem number 5. Now let's take a look at number 6. We have a Maclaurin series for the function f is given by this right here. And they did do a partial expansion of this, which is semi-helpful, as you'll see in a second. And it's going to converge for f of x for the absolute value of x less than r, where r is the radius of conversion for the Maclaurin series. First thing they want you to do is find r. Okay, and they actually tell you to use the ratio test. That's kind of redundant, because we know we have to use the ratio test to find or we want to use that ratio test to find r on that one. So in this case, that's worth 3 points. You get 1 point for just setting up the ratio. 1 point for calculating that ratio, simplifying that, calculating, finding the limit, and then 1 point for the radius of convergence. So you have that. Next one, write the first 4 non-zero terms of the Maclaurin series for f prime. Okay. The derivative of f, express f prime as a rational function. So in this case, you really have 2 options. Option 1 is, f of x here is equal to that sum where n equals 1 to infinity of -3 to the n minus 1 over n times x to the n. You can take the derivative of that. You work with that. Or do the expansion. Now you'll notice that they've done 3 terms. We need to go 1 more. So get that expanded to 4 terms, and that would work as well. But they want you to go through, write those first 4 non-zero terms for the Maclaurin series of f prime. If you want to go further, you can. The derivative of f, and express. Then they want you to express f prime as a rational function for x, the absolute value of x less than r. All right, so what happens on this one? You're going to want to write that out, okay? And then you're going to want to look at what's true. You get those first 4 terms, that's fine. If you want to go more, you can. But you got to keep in mind that that's going to be that there's a generalization that can take place in terms of these terms. And you're going to want to look at those terms that you have and determine that generalization, i.e., you're going to be able to tell me about this series that you're working with. And from there, once you have that, then you're going to be able to use that information to go through. You should be able to use that information to go through and write f prime as a rational function. So you're going to want to have f prime of x is equal to something involving x's. There won't be any n's left in there, okay, when you do that one. And then the next one, write the first four non-zero terms of the Maclaurin series for e of x, e to the x. Use the Maclaurin series for e to the x to write the third degree Taylor polynomial for g of x equals e to the x times f of x. So really what's going to happen on this one, you've got to go through and do the multiplication and simplifying. You want to get those first four terms done. So you're going to want to multiply that, or in this case, you want to have the third degree. So once you get to a third degree, so you have x, you're done with the x cubes, you're done with the x cubes, then you can stop, but you want to go through and do that multiplication. And it's really going to be a matter of foiling, if you will, however you write it out. We wrote it out one way. You could write it out as e to the x on the top, f of x here, and so you're going to have e to the x there, you'll have f of x there, and then down below it, you'll be able to go through and just say, okay, I'm going to take the first term of f of x, multiply it by everything, the second term of f of x, multiply it by everything, the third term of f, so forth, until you get down to where you're not dealing with a cubic, where you've gone beyond the cubic, and then simplify it. So it's really up to you how you do it, but you want to get that, and then they want to see that third degree Taylor polynomial for the product of those. So that's the next part. So with that does cover everything that we have to deal with for this particular one. I hope this video and the other one has helped. And we will see you in class on, what would it be, on Wednesday? So that's when this will be due. So with that, I hope you are still enjoying your break, and we'll see you on Wednesday.